This video is going to talk about an application of trigonometry. Mostly it's going to deal with right triangle trig, but sometimes in right triangle trig we have some real world stuff that gets in the way. So a great application of right triangle trig is dealing with what we call bearings. If we're talking about sailing or nautical things, or if we're talking about flying or air navigation, a lot of times we have to deal with bearings, right? Dealing with north, south, east, and west. And the two typical ways that we measure bearings, again, are basically to either measure it from either north or south, so such as the two angles we have over here on our graph. Notice that the red line is not measured from 0 degrees or standard position 0 degrees as we normally would. We're measuring from the north to the west. And it's kind of a different way of writing that. And from the north to the west, 15 degrees. So if due north, right, is our y-axis here, this angle, this small angle here, would be our 15 degrees, right? From the north directly to the west, right? To the west over here, exactly 15 degrees. The purple angle down at the bottom, same idea. We're measuring from the south to the east, right? But notice where that angle is drawn, directly from the y-axis, where we normally wouldn't draw angles, right? If we were doing reference angles or standard position angles. But again, we're measuring from the south to the east, exactly 70 degrees. So again, those would be how we would typically measure nautical angles. From the north to the east or west, or from the south to the east or west. Will never be more than 90 degrees, because again, if you enter a different quadrant, you know, if I moved up into quadrant 1 over here, well then I should be measuring from the north to the east, rather than from the south to the east, right? So again, we'll never pass that quadrant. We'll never pass that x-axis, right? Now, air navigation is a little bit different. We go clockwise from the north, right? Air navigation would go clockwise from the north. So again, if we were measuring this purple angle down here, right? And I'll have to draw it with a different colored line. I don't have purple, or actually I think I do here. Again, we would measure it from the north all the way clockwise down to our side length here. So again, if this is 70 degrees down here, well, 180 degrees, right, from north to south, straight line, minus that 70, this would have just been a 110 degree bearing. And notice I don't necessarily have to say from the north, because again, if we're talking air navigation, everything is measured from the north. So 110 degrees would just tell me from north, go clockwise, 110 degrees. Right? If we were dealing with that red angle, right, we would technically go all the way around here, right, to get all the way there. And again, the only thing we don't go is that 15 degrees. So again, that angle would have been a 360 degrees minus that 15, or basically 345 degrees from north, clockwise from north. So again, when we're talking air navigation or a lot of the air navigation problems that we deal with, they may just be measuring from north all the way around the circle to wherever you want to stop. Really, we shouldn't go greater than 360 degrees there, because again, if we go past that north, then we should just measure the small reference angle, right, or the small angle there. Let's look at a couple of problems here. So notice this one's dealing with ships, so we're talking that nautical navigation. A ship is 90 miles south and 20 miles east of port. So again, we're going to be 90 miles south. Here's the port up top, right, and here's the ship. We're 90 miles south and 20 miles east of the port. If a captain wants to travel directly back to port, what bearing should be taken? Well, from the ship, right down here at this bottom side, remember that nautically we're going to measure from the north. So I'm going to draw a line straight north here, right? That's due north. What I really want to find is this angle here. But since that's not inside my triangle, let's go ahead and find its partner angle. Why don't we go ahead and find theta down below here? And then we can always subtract theta from 90, right, to make that right angle. So let's go ahead and start with the fact that, well, theta is opposite the 90. It's adjacent to the 20. This is a great time to maybe use a tangent. So again, the tangent of theta would be equal to 90 over 20. In order to solve that, we're going to take an inverse tangent. Right, on both sides, we'll cancel the tangent on the left and take the inverse tangent of, well, 90 over 20 is really just 9 halves, right, or 9 over 2. So it might be a little bit easier to write it that way. So let's jump over to our calculator real quick here. And what I want to do is make sure when I get on my calculator, again, if we're going to deal with nautical things, we're typically dealing in degrees. So let's make sure we're in degree mode here. Notice up top, my calculator shows me immediately I'm in degree mode. If yours doesn't show you, make sure you go to the mode, check that out. Because when we type in an inverse tangent, right, again, of 9/2, whatever mode we're in, inverses find angles, that's going to find us an answer in degrees. So it looks like we're about 77.471 degrees. So 77.471 degrees. But now remember, that's not the angle we wanted. That was theta. We need this angle up top. Let's just call it alpha real quick here, right? And again, alpha plus theta right now would be equal to 90 degrees. So let's go ahead and say, if we want to find alpha, let's take 90 minus our theta answer, right? 90 minus that angle. So hop back over to the calculator. Let's make sure we're nice and precise. 90 minus our angle. And it looks like 12.529. We are going to be 12.529 degrees. And again, that's from the north. And we're going to the west this time, right? Again, the ship is east of port, but we need to go back to the port. So we need to travel to the west, those 12 degrees. And that would be my answer to that first question. If he wants to reach the port in 1.5 hours, how fast does he need to travel in nautical miles per hour? Realize that if they ever refer to knots, we're talking nautical miles per hour, right? Which essentially is miles per hour. Well, we know that, again, the direction straight back to the port is just going to be our hypotenuse here. Let's just call it h. We haven't used that variable yet. And so if I can find the length of h, we need to reach port in 1.5 hours. I can divide my miles by my hours, right? So a little Pythagorean theorem, 90 squared plus 20 squared. Right? Pythagorean theorem is still right triangle trigonometry technically. It works with right triangles. So h would be equal to the square root of, right, 90 squared plus 20 squared. And then what we're going to do is divide that h by our hours, right, or by our time. So let's divide that by 1.5. And let's go ahead and hop on the calculator and we'll figure that out. So again, the square root of 90 squared plus 20 squared, and then we're going to divide that number by 1.5, and we are going to be at 61.464. 61.464 knots, or basically miles per hour, right? Our distance over time there. Let's do one more bearing problem. Again, this one we're dealing with aviation. So notice up top here, an airplane is flying 550 miles per hour and at a bearing of 195 degrees. Well, remember, that's a bearing, right? If we're looking at it clockwise from north. So if we're looking here, we're going to be going around, right, from north clockwise 195 degrees. So we're going to be traveling this direction, right? Down there. And it might be easier to take off that 180 degrees. 195 is 15 degrees past 180. So that could get us a nice triangle going on there, right? That should get us a nice triangle. We're going 550 miles per hour, but after flying 2 hours, how far south? So basically we're looking for this value here. How far south has the plane traveled from its point of departure? Well, the plane is flying along the hypotenuse. It's 550 miles per hour for 2 hours. So I would say that 550 times 2, right, is going to be our distance. So that's 1,100. So that's going to be 1,100 over here. And remember that we're looking for y over here on this side. Well, again, that's adjacent. That's hypotenuse. Sounds like a cosine might be a good idea for us. Cosine of 15 degrees is going to be equal to adjacent over hypotenuse. Y equals 1,100 times the cosine at 15 degrees. And for us, our distance to the south, right, on there, our distance to the south, sorry about that, is going to be calculator, right, 1100. The cosine of 15 degrees. So 1062. Okay. 1062, because notice it says to the nearest mile. So actually, let's double check our decimal one more time. Oops, would have been rounded up, right? 1063, we'll say. Right? 1063 miles. I hope that helps you with some bearings when you're talking about right triangle trig. If you have any questions, talk to your teacher. Otherwise, have a great day.